section design and quick layout. And that's my quick layout. It's my favorite one. You can also get to the chart title, click on all this stuff. Yeah, also, I'll show this again real quick. Got all these options, got so many cool things, it's so nice.
Gary! I was just looking for the sports.
Who is all here? We can do some review. We'll see if anyone's in the chat right now. Office hours. Do we have... It says 74 seconds in. I thought it said 74 people watching. I was like, 74 people watching? No way. Let me reload it and see if we have anyone. It shows me people are in the... One person watching. It's just me. Well, it's the day of the test. Let's see if anyone joins in and has questions. We can review whatever chapter you want right now. So whatever chapter people want. So many things going on in the world. Oh, it's the birthday thing. Oh, it's from 2 to 3. There's a birthday thing. Not mine. Anyone here? Bueller? One person, still just me. Only me here. What is a private video again? Should know it's public. Oh, 4 people. Hey, we've got 4 people in the chat. If you have questions, ask away. You can say whatever chapter you want to work on. Whatever chapter you want to work on. Name the chapter, we do the work. All I'd say is, help me understand this chapter, and we'll start working on it. You name the chapter, we do the work. That's the name of the game right now. What chapter, what work? Chilling out. What chapter, what work? You name it, we'll do the work. I might start work here in a moment. I'll probably start up the work. Who has a question? Who has a question? You pick. I think I might have to pick a question. Let's go check out. Here we go. Hey, look at that. Right as I click the button. Chapter 5, Chapter 6. So Chapter 5 and Chapter 6 are over the normal curve and also over correlation. So let's do Chapter 5. Good one to start on. Chapter 5. 353. Chapter 5 review. We'll try a few different things. I'm going to write 5 questions for this chapter. See if you can solve all 5. 1. Why is he mad about this? No, it's a question. And see if you can solve these, Alexis. We'll solve each one of these and I'll explain the solve. Some of these are pretty simple. Some of these are a little more in depth. Think of another one that follows this. Yeah, that's what we're going to do right here. This one of these is a percentile one. So we'll make sure we cover that alley in depth right here. What's the answer to the first one? Yeah, and then we'll do that too. Let me add that. Ali will do Ali's question, which is categorical or quantitative displays. We'll do that next. So the first one is false, because you first have to look at the shape of data, which maybe we should do this one next. Like in the order by which these questions go, it makes more logical sense to talk about how you would check it. So the answer here is false. The data must follow the normal curve to use things like the 68, 95, 99.7 empirical rule. You can't use the normal data. Some data is very skewed. You can't use normal model on all data. Frankly, it works better with things like the central limit theorem. That's a topic for another day. And I think you figured out number 2, which was number 2, now it's number 3. And here we'll go to that one here in a moment. But Alexis has already figured out problem number 3, was number 2 a second ago. How do you check the normality of data? So there are 3 ways. The 3 ways to check the normality of data is you can look at a, here we'll do in bold, look at a histogram. does it follow the normal, which is unimodal, one mode, / symmetric? Or is it skewed or has outliers? What's another way to check normality? One way is to just look at a histogram. You look, and it should look something like this. That's good enough. The little deviations from normality,
It doesn't matter.
like that's good enough, probably. Mostly normal, we'd say. What's another way to check normality? What is another way to check normality? Another way. There's 3 ways. You can look at the histogram. You can just make a histogram of the day and see if it looks normal. And that guy would be all the way over there on the far end of the curve. What's another way to check normality? Anyone know? I'll answer in one moment. We'll throw some points here. We have a few answers. What's another way to check normality? You get like 10 more seconds. The more you can answer it, the better. The more if you don't know it, though. You can always say, I don't know, and I get points for that, too. So we have a normal probability plot. And this is a plot that shows our data compared to the normal. Kind of the curve, it's more of a line. And does it follow the line? If it follows the line, it's normal. If it bends away, it's not normal. So what you want it to do is you want your data to follow the line. This isn't a linear model, so to say, but you want your data to follow like this. Like this would be normal. I'm only doing what looks normal. If it's not normal, it doesn't follow the line, which the line dictates what's normal. The last one is where you fit something over it. Does anyone remember the name of this one? So the last one, and feel free to answer in the chat, what's it called? Like the more you remember it, the more you say it, the more you remember it. If I say it, it's one thing, because I've said these things a few times, but don't worry, it's practice. What is the last way to check here called? And then we're going to do quantitative and categorical displays next, but put your questions in the chat. And try doing these little mini drawings too. The last way is a goodness of fit test. And uses a p-value to see if it is a good or bad fit. High p-value indicates good fit. Low, less than 0.5 indicates bad fit. And so with this right here, if this is good, which is a good fit, you'd have a normal curve. And if you fit this over top the data, it fits pretty well. You can move it around a little bit. It's still a normal curve. Fits pretty good fit. Not perfect, but pretty good fit. And since the normal curve is a good fit, when we do the test right here, we'll be doing the chi-square. Well, there's the chi-squared goodness of fit. Good questions, Allie. Maybe done a little bit of stats right there. There's the chi-squared goodness of fit test. I think it was with the certain. I don't use the goodness of fit test much. I use the chi-squared, just general chi-squared test of independence, and there's a chi-squared goodness of fit test too. And I'll show you that just briefly here. Let's talk about that just briefly. This would have a high p-value. So what you're actually looking at, the best way to look at the test is the Canvas content. Canvas content is the best way. Practice test is pretty good. Canvas content is #1 way to know what the test looks like. What you need to think about is the chi-squared is just another shape of a distribution. So you can see if this fits your data, and that's why it's called the chi-squared goodness of fit. So think about this. You could actually have skewed data and see if the chi-squared fits it, and you could see if the chi-squared is a good fit. Do you think after you saw what the chi-squared looks like, yes or no, do you think the chi-squared could be a good fit for this data down here, which is a different test? But do you think the chi-squared distribution, there it is, chi-squared distribution, is maybe a good fit? Like you see it's got that right skew shape. Do you think it's maybe a good fit for this data? Maybe it is. And that's a different test. That's the chi-squared goodness of fit. We're seeing if the normal. So this whole idea of goodness of fit is about seeing if the distribution shape that we have, like the normal, is a good fit on the data. So there's, if you've maybe heard the goodness of fit test, Allie, there's all different goodness of fits. You could test like a Cauchy distribution, geometric distribution, binomial distribution. You can see if there are other good fits for the data, and sometimes people do that to see which one's a good fit, which ones are bad fits. So that's why we call it a goodness of fit. You take the shape of the data and you see if it fits over it. Mathematically, we do it, but that's kind of the way it's done. It's seeing if it's a good fit. If the p-value is high, it's a good fit. Same thing for the chi-squared, a goodness fit. If the p-value is high, it's a good fit. P-value is low, it's a bad fit. A man finds out last month his electricity bill was $400. So what is that in notation? We hadn't heard from Leo a lot this semester.
Notation.
But what is
brother.
400 in notation? Great job, Allie. Have you done that in like a biology class or something? Usually where you see things like that. What is 400 in notation? In notation, 400 is what? Notation really helps for later in the semester. It helps now, but AP Stats. Shout out to AP Stats right there. Let's throw them 1,000 points. There's like the normal goodness of it. What is 400? That's how much he spent last month. So what is that in notation? If he spent 400 last month, that is an observation. And then, come to find out, he hears from the electricity company that the average is this. That is mu. And last but not least, we have sigma, which is standard deviation. So you do observation minus mean over standard deviation. And that leads to the z-score. And so it's going to be 400 minus 250 over 50, and that is a z-score of 3. What percent of people are expected to pay more than him? Does anyone know the answer to 4 pretty quickly? I'm going to pause on 4, but this is where you want to draw your curve. A test question would say, it would say like this: use the 68, 95, 99.7 rule. The test question would explicitly tell you or give you a picture until you use this rule. We'll do that right there. So what would the test question, what would be the answer? Little drawing would really help here. Little drawing really helps. I'm going to see if anyone gets it, and then I'll explain the answer. What would be the answer? Start drawing. Close, very close. Very, very close. There's a small decimal difference. Very close. John's got it. Great work. Teamwork right there. 5,000 points together. We know where the z-score is at. We know this is the z-score of +3. So that's the observation right there. That is the observation. And then we do the 68, 95, 99.7 rule. And we see that 99.7 is contained within this right here. And we want to go below here. Oh, more than him. More. Whoops. So if we're going more than, it's this tail right here, which is this tiny little bit. And so that's 0.15. And then you can also do the remaining out here, but we're only interested in this area right there. So it is 3.3% outside. Yes, Ali corrected it right there. That makes sense. And this leads to a follow-up question. What percentile, good to see you, Brandon and everyone, what percentile would they be in? What percentile, this is like a follow-up question now, which we can use this graphic and everything. What percentile would this person be in? What percentile would this person be in? Does anyone know what percentile they would be in? Ah, yeah, you're on the right track. So if you notice what I did right here, I lost my little lines on this. What percentile would they be in? They'd be in the, well, and I just say the answer and you got it. Yep. Close, Alexis. Double check your math. Double check your math. Double check the math. Good to see you there, Taryn. It is the 99.85th. Because 99.85% of the data is below this point. Below this point. And you can also check that 0.15 is above it. Does that make sense? So that's how you can check your answer right there. It also coincides with the previous answer up there that 0.15 is above it, 99.85 is below it. And that's Brandon, that works there too. Good answers, Brandon. So that's how percentiles work. Percentile is, always say it with me, the area below a point. Not like that's a test question, but the percentiles are always area below a point. You have to add up all the area below it. You can also subtract the area above it. That's another way to get the answer, is to take the area above it and subtract from 100 to find out the area below. So do remember, area is percent below someone. On the test, do you want to be in the 90th or 10th percentile? I mean, of course, we'd like to be in, like, you know, would you rather be in the 90th or 10th percentile, which is a good way to remember where percentiles are on the curve. That's why I ask questions like this when you think, on the test, I want to be in the what percentile. What percentile would you like to be in on the test? And then we're going to do categorical and quantitative displays next. Getting ready for the next question. You'd want to be in the 90th. Good answers right there. I'll throw you some points. You want to be in the 90th? And so don't worry, you get points all around here. Because the 90th is over on this side, the right side of the curve. The 90th is going to be the high side of the curve. So if you think about a test, if the mean is 70, you'd be over here towards a 100 in the 99.85th percentile. And then you could figure about where the 10th percentile is going to be about here-ish, I believe. The 90th percentile is going to be about there. So that's where the 90th percentile would be, which we can do this. Let's say this. Here's a follow-up question. Are you ready? I'm changing this one. So see if you can solve this. Really? I didn't want it to, okay, I don't want it to destroy the text. Good. Here's the question. The z-score for the 10th percentile is 1.28. What is a 90, what score okay, so does everyone see this right here? Now I'm giving you things on the test, like if you saw a graphic like this and it had there's the mean. So mean is this, and then we're going to do graphics right after this. Sigma is 10 because that's the unit difference. So the unit difference is always the standard deviation, and then the mean is at the center of the curve. And so the unit differences are the standard deviation between each mark on the curve for the z-scores. So does anyone know the answer to this question right here? The z-score for the 10th percentile is 1.28. Oh, negative. Sorry. Kind of gives away where I was going with the question, though. So although I'm running out of room, I'm going to put it up above where this is at 0, this is at 1, this is at 2, this is at 3, this is at -1, this is at -2, -3, tracing down below to the numbers. Who knows the answer to this question about what is the score of the 90th percentile? If we draw on our curve right here, you'd be about here at 1.28 negative. And the question says that this is the 10th percentile, which means 10% of the data is below here. Who follows the question so far? Who follows the question so far? Are people following along? Let me know if you're stuck. So this might be what it shows you on the test. Correct. Well, that's z-score. Great with Taryn right there. That is the z-score. So that wouldn't be the score yet. It says, so what is the score? Like, what did they make on the test? It should probably clarify, like, what is the score on the test? Like, what did they actually score? And if we look, and I think Ali and everyone's doing a great job, teamwork right there, is this would be a z-score of positive 1.28. And you can see about where the answer is. It's somewhere in here. And that can help confirm the answer. So you would need to then take, I'm going to erase the previous answer so we can get a little more room to work. If you know what the z-score is, because this is the top 10% over here, there's 10% of area above here. If there's 10% of area above this, that leads to 90% below here. Because it's symmetric on this, that this is the same 10%, but on the other side. So we can just delete it. It's just flipped exactly. And so now you can go, and with this, we know the z-score of negative 1.28. So on the other side, we'd go up 1.28 standard deviations, which are 10, and we would add that to the mean of 70. So that's the mean plus z times sigma, which is a reworking of observation minus mean over standard deviation, which leads to a z-score. And this is going to lead to 82.8 right there. So that will be the answer, and that is equal to y, the observation. So there we go. That's how it works. Is that, I think people understand. They see how to solve these problems. You want to make sure you understand what a z-score is. That's how many standard deviations above or below the mean something is. And good work right there. Let's do some categorical and quantitative displays. Okay, so what we're going to do is we're going to list all the displays. All the displays. So what is the first variable type we dealt with? I'm going to do all displays right here. I mean, from what we learned. What is the first variable type we dealt with? We'll do variable, and then we'll do display and summaries. What's the first kind of variable? So you got to know the two types of variables. Do you remember the first one we dealt with? What's the first kind of variable? You're right, Taryn, 5,000 points. Categorical, you got it. So categorical, excellent work. Categorical. What is a categorical display of data? Or we'll visualize it here. A small visual of it. What is a categorical? And all the answers are on the screen. You're probably going to pause it right here. That is all the answers to every single question I'm about to ask. Aiden, we're going to throw you some points. Histograms are quantitative. They are a quantitative, but we threw you some points for that. You're right. Make a pie chart of your favorite bars and bar chart of your favorite pies. So pie charts and bar charts. And then usually, and we'll do a little drawing over here. A pie chart looks like this. Bar chart. Really. And then a bar chart. Bar chart is, we don't even have to go over there. We can just draw it. Bar chart has the bars, and there's separation where it has like the thing below it. You'll see the difference between it and a histogram, because what are other displays? Like if you put the bars in order, what do you get? If you put the bars in order, what do you get? If you put the bars in order, what do you get? What's a special case bar chart put in order from most common to least common? Pareto. Nice job, John, right there. So Pareto, put the bars in order. Remember, Pareto, put the bars in order. And it's, you probably have more categories than two, because that's technically a Pareto up there. But Pareto is the bars put in order from most common to least common. And you just have like freshman, junior, sophomore, senior, or something like that. So I know that's an ordinal variable, but it's set up in a Pareto chart. We also have frequency table. A frequency table shows you the frequency at which things occur, such as you could just have cat and dog, and then the frequency would be like how many observations. That's not quantitative right now. It's a frequency of how often things occur, like cat and dog. 10 people had cats, 20 people have dogs. Because you have to ask what kind of animal do you have. I'm pretty sure that's it. I'll double check. But a ring chart's just a pie chart with the center cut out. No one likes them. That's why sad face is there. What was the next type of variable we dealt with? You should know this. It's actual real numbers. It's the next type of variable we dealt with. What is the next type of variable we dealt with? The next type of variable we dealt with was what? What's the next kind of variable we dealt with? The next type of variable we dealt with. What was that? Quantitative. More points in the chat. Quantitative. Quantitative are actual real numbers. And you can also call categorical qualitative. I hate that word. So what are some quantitative displays of data? What are some quantitative displays of data? I'm going to give myself more room when I draw on this time. Give me a quantitative. All the answers are on the screen in the top left corner in blue. There. Histogram. Now we're doing histograms. So when you do a histogram, and this is a good way to remember, histograms analyze what. When you make a histogram, you analyze what of it, which we got a monster man here if you can't tell. You analyze what of a histogram? What do you analyze of a histogram? And John's got box plots. Nice job. What do you analyze of a histogram? Shape, center, spread. So you got the right skew monster man, right to the high, left to the low, whatever way the monster man's tail goes. So you can look and see it goes to the right high side, and that is a right skewed monster man. If its tail goes to low side, then it is. Shape, center, spread. Shape dictates center and spread. Make sure to know the differences between different shapes, different centers, and different spreads. A box plot is a visualization of what numbers? A box plot is a visualization of what numbers, which also means it's quantitative. A histogram also has a quantitative numeric line below it. That'd be bad if that was tested. Maybe that's push-ups people can do. That's better analysis. A histogram, a box plot, is the visualization of what numbers. For this data, it would probably look something like this. We're drawing the analogous box plot below it. That's good enough. That's about right. Maybe we didn't do everything perfectly. The quartiles, the 5-number summary, the min, the Q1, the median, Q1, the Q3 at the top of the box, and the max, which don't forget outliers, because the max could be an outlier and the min could be an outlier. The fences, which we don't see, they're just a graphical technique. The fences that we don't see are 1.5 IQRs above Q3 and 1.5 IQRs below Q1. So that's Q1 minus 1.5 IQR. And the IQR is the box itself. That is the interquartile range. There's a lot of you right here. But how do you tell the skew of a box plot? The way it's stretched out. Yeah, good question, Charlie, right there. So if you look at a box plot and it looks like this, it looks mostly what? This box plot, think of an S word, looks mostly, I could do a little better. This box plot looks mostly what? Box plots are not the best for shape. They usually hide the shape. Histograms are the best for shape. Box plots hide important features that histograms show. So that box plot looks mostly what? Symmetric. Great job, Charlie. So what can happen in a box plot is when you have a box plot, the distance between the lines themselves, like this is the min to the Q1. Well, what if all of a sudden to the median is the same difference? This is 50% of your data now. 50% of the data is contained down here, but the top portion of the data goes all the way up to here to Q3, and then all the way up to here. So think about this. The top 50% is more spread out, which is analogous to this data over here, where the bottom 50%, the min to Q1, is less spread out, and the top I'm blocking it, is the top more spread out. So the way you see the stretching between the quartiles is going to be like when there's bigger distances at the high side, that's right skew. If you just were to flip this, bigger distances on the low side would indicate left skew. That did not work. Bigger differences, and I'll do a left skew one. I mean, it's just the reverse image of it. Because then you would have the data more compact on this side, and then you'd go down to the median, and then you would stretch things out a lot more. You go wee like that, and then it's more stretched out. And then this would indicate a very left skew data set, which would look something like this. There'd be a lot of data here, like 50% of the data is above and below that line. Does that make sense? How you can look at a box plot and you can see where the median is at, and is the low side more stretched out, or is the high side, because it's all compact up here. This is 50% of the data right here, like this is 50% down here. Both of these have the same amount of data in them. It's just the low end of the data is more stretched out. What are the two graphics we don't mention as much? One of them shows you the numbers. There's two additional graphics to talk about here with quantitative data. What are the two additional graphics? Whoops, really? Don't do that to me. There we go. What are the two additional graphics? I don't love them as much. Sorry, graphics. Dot plot, and stem and leaf. So stem and leaf and dot plot, not that important, not that big of a deal. Dot plots are like that same histogram up top, except in a dot plot, you just draw dots. You go dot, 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 dot. They're not scatter plots, which will be coming here shortly. You just draw dots. You can see how many dots there are. They represent the height of the frequency of like how many observations there are. Like this can have a frequency bar too for like 10 observations, 20. It's not bivariate data, it's just the count of observations. So each of these shows you a count of observations in that group. A stem and leaf is like a dot plot or a histogram, but in a stem and leaf, you actually see the numbers, where you have like a number line down here, and might be something like push-ups or something, and you could have a bunch of zeros, some ones, some twos, and 6 and 7, and then this would be 12, and usually have a key that says something like 1-2 equals 12. So then you would know if you see this, you go to the stem and the leaf, and you can see what it is. So that's a stem and leaf. Now we switch over to, let's do cat. What are categorical displays of data? So we'll write cat. Cat. What are categorical displays of data? See if you know, see if you can answer. Good answers in the chat, good practice. What are categorical displays of data? Let's go to a new page because we're bivariate now. Yeah, you can just side-by-side pi. You can do that. Anything else? Side-by-side pi is technically correct. We don't use a lot. Stacked bar chart. We use that some. A lot of people use that one. And then we get into the big ones here. Contingency table, probably the biggest one. Contingency table and mosaic plot. So Mubot, it's testing, man. You got to lock in Mubot. So side-by-side pie charts, you just put an extra pie chart side by side, and you can see differences. Like one group might have more of one. Stacked bar charts are where you take your bars and you stack them. And so stacked bar charts can look like this right here. They look a lot like mosaic plots. It's just mosaic plots have the continuous axis down here, showing you the marginal display and the conditional displays. So we really like the mosaic plots a lot more. And a contingency table, there we go. A contingency table is where you actually make a table, and the table has in it the values for things like pass, fail, study, no study, and then you can put like 200 students total and 160 passed, 40 failed. There were how many students who did not study? There were 30 students who did not study, 170 who studied, and then the students who passed who did not study was 10. Everything's solved now. And there we go. So you can see like the pass fail rate of study not study, and the graphic down below is not perfect. If it were the same, okay, we only had 30 students who did not study, so it'd be something like that, because that should be 15%, because 30 out of 200 is 15%. I'm looking down here at the bottom display, and then 2/3 of them failed, so it'd go up to there, and then a little more than 10% of the students failed, about 11.3% failed or so. So it's gonna be right there. So this would show you the fail rate and the pass rate for students who either did not study or studied. Does this make sense to people right here? Who feels like they follow along? This same thing could be graphed in these graphics here. If we make it the same data, you'd have the pie chart of the students who didn't study, and the fail rate would be like this. And then you'd have the pie, so this would be the no study pie chart. This would be the study, and fail is the dark color right there. And then the failure rate of the study group would be something like this. They're kind of inverse of each other. And then we would have a stacked bar chart, very similar to, it's just the same plot below, but doesn't have the conditional access. So this would be the no study group. Sorry, I reversed it in the bottom graphic. And then this would be the study group right here. It's going to look just like the bottom one. Do people feel like they follow? That each of these graphics right here shows you, and this is the no study group, and this is the study. There you go. That's got it. Okay, so now we go on to cat quant. So categorical X, quantitative Y. And maybe we'll specify the X. What graphics do we make here? What is our top two graphics for categorical X, quantitative Y? Categorical X, quantitative Y, right here. What are our top two graphics? Any ideas on these graphics? What do people say? Side-by-side box plots. The idea of side-by-siding just means adding more side-by-side box plots. And stacked histograms, yep. Truthfully, you could do things, don't mention it, but you could do stacked box plots, and you could do side-by-side histograms. I wouldn't, but you could. Side-by-side histograms. So when you do side-by-side box plots, if you look, the box plots are the quantitative aspect of it, and then the side-by-siding puts it in the different groups. The same thing for stacking and stacked and side-by-siding. The histograms themselves are the quantitative aspect of it, and then this allows you to show more groups. So when you do side-by-side box plots, you just do something like test A versus test B, and you can see test B has a higher median and higher max and everything. So you could do test A versus test B. And you'd have a quantitative axis over here like 80 to 100. Side-by-side stacked histograms, excuse me. You put them on top of each other. So this is the stacking aspect of it. You draw a histogram here and a histogram here, and then you can compare the shape more easily. Should they have the same axes, yes or no? Should they have the same axis? The same axis, yes or no? When you stack histograms, should they have the same axis? You'd be like, ooh, whatever group this is, if this is group A versus group B. They should 100% have the same axis. They should totally have the same axis. Stacked box plots, you literally just take this graphic right here, and I'm not even kidding. You just You just do this. It's gonna look horrible, but it's literally just the way you're doing it. Does that make sense? I can redraw it, but I guess I probably will. You just go and you make box plots like this. You stack them. This is the idea of stacking right here. This is stacking, and the other one's side-by-siding. So these are stacked box plots now. They're just stacked on top of each other. So stacking means to put on top of, and then side-by-siding means to put side-by-side. So you can do side-by-side histograms. A lot of times people do, when they do side-by-side histograms, I hate it. So I usually see stacked histograms. They usually do side-by-side histograms like this. So you could compare the differences. I don't see many side-by-side histograms. Then you'd have like the number line. But that's side-by-siding. So once again, you would just take this graphic and turn it like that. So it'd be side-by-siding. Does everyone think they understand the difference between like the idea of stacking or side-by-siding? On the bottom, what does that mean? That means different amounts for each group. Yeah, good question on that one right there. And so the stacking and side-by-siding means we're adding groups, and the box plots and histograms are the quantitative. And to Charlie's question right there, when you're talking about the mosaic plot on the bottom, what is this area called on the mosaic plot? The what distribution? What is that called? Just like with the plot down here, the contingency table, that's called the what? That's the what distribution. That's the what distribution. The marginal, Logan on fire right there. You're right, Logan. That is the marginal distribution because it's in the margins. Great job. And so this means a lot more students studied versus not studied. If you see the amount that's studied right there, nice job. So that's the marginal. It represents one variable, emoting. And you could also put a marginal over here. Sometimes people put like a marginal here for the pass-fail rate, and the fail rate would be for the overall test here. And this would be representative of this number here of the overall all students. So people sometimes do that and have a marginal display on the side of the table. So you can see marginal displays over there. Okay, let's do the last. What is the last combination? We've gone over literally every graphical display right here. What is the last combination of variables? What is the last combination? We've done categorical. We've done quantitative. We've done categorical. We've done quantitative categorical. There are other ones, things we don't cover in this class, like logistic, not covered, but quant. So we got quantitative. So we got quantitative/quantitative. And what is our number? Sure, I thought I misspelled it. What is our number one display for quantitative? The number one display for quantitative is going to be a what? Was the number one display scatter plots. And so scatter plots are the visualization of two quantitative variables. You can't make a scatter plot unless you have two quantitative variables. And so you go right here and you draw your number line, and this could be like height and weight. So if we're looking at height, we're looking at something like 50 inches to 80. If we're looking at weight, we're looking at like 90 to 300 or something. So, whoops, there we go. And you probably have a mostly linear, some outliers, mostly linear relationship right here. So the scatter plot, if we look at somebody's weight versus height, you can see a positive linear relationship. This value is measured by what is called Pearson's correlation, known as R, which measures the strength of linear relationships. So this might have a Pearson correlation of R of something like 0.44. Who knows what it is? But the tighter it is, like if we remove some of these outliers here, that would increase the value of correlation because there's a stronger linear relationship. So now we're not at 0.44 probably because we removed a bunch of outliers and it follows the line a lot better. We're probably at something like 0.72. Who knows? You only achieve perfect correlation, and I'll have to kind of redraw this completely to do this, but you only achieve perfect correlation when every point is where? You only achieve perfect correlation when every point is where? You only achieve perfect correlation when every point is where? On the line perfectly. It can have no deviation. So what is one of the values of perfect correlation, which this one is shown, which doesn't really make sense. Great job, everyone in the chat. What is one of the values of perfect correlation? What is one of the values of perfect correlation? There are two values. This relationship doesn't make sense anymore, but visually, what is the value? 1. 1 is one of the values. This one's not a correlation of 1, though. And -1. You are correct. And that's, yeah. 1 and -1 are the values of perfect correlation. So does this mean that, and I always love this. You could go out and collect data from two people. And if you collected data on two people, you would get a perfect, likely positive correlation between their height and weight. So think about this. Does this mean that if we could reverse it, so we could do weight and height? Think about Brian wants to be in the NBA. If Brian gains weight, will he get taller? If Brian gains weight, this has an R of 1. If Brian gains weight, will he get taller, yes or no? Do remember, I'm in my 40s. Puberty is a long time ago. Really, Logan? Really?
I am Mubot.
You're right, though. You're right. So even if you have a correlation of 1, it doesn't show cause and effect. We don't use that cause word around here. Mubot will freak out if I say it. Mubot, you want to talk to us here, Mubot? You want to say hey?
Brian, stop it. I will call you out in the chat for that. That's a bad word.
And we get a Mubot. Correlation is not causation. It's because there's a lot of times confounding variables, or we didn't run an experiment where we randomized and did an element of control. You can't say, even with a correlation of 1, that it shows causation. You just say there's a strong association with a correlation of 1. And then someone would say, but you only ran 2 points. You'd be like, yeah. And they say, well, that's not statistically significant. You can't even calculate significance. You say, yeah, you've taken stats. So I always say the stats don't lie. The statistician does. That's on one of my cards here somewhere. Mubot even knows. You can use stats to lie, and you shouldn't. But there's a lot of things people don't understand about statistics, and it comes back to bite them, because if you don't know stats, you don't know what you're doing with stats, and you don't know if people are misusing the stats. So another graphical display, which is when you put time on the x-axis, is called a what plot. Another graphical display of 2 quantitative variables is when you go down here and you put maybe the year, like 1990, and then you go here to 2025, and you do like milk in dollars. .com burst, housing market crisis, COVID. So there is a time plot. Time plot right here is the price of something over time. One thing, I was just randomly making dots. Just like that. Wouldn't that be a category of years? Could you say that? It wouldn't be categorical, though, because year is quantitative. Can we subtract, like, imagine you say, let's say you say, I'm born in 2004, and you say, but my parents are born in 1980. So it's maybe when your guys' parents, I don't know anymore. There would be 24 years difference, which makes it a quantity. So the way to check if something's numeric or quantitative is to see if you can do mathematics on it, and if the math makes a sense when you do it. So a time plot uses a quantitative time variable as the x variable, and then a quantitative y variable to analyze differences over time. So that is a time plot right there. I should have wrote time plot on it. But that is a time plot. Time plot, which is a special case scatter plot. Really? Scatter. Well, it's a little birthday get-together going to happen. Time plot, special case, scatter plot. Any last few questions? This was a good kind of quick review. We went over, that was longer than I thought for that. This is a bunch of chapters right here. If you look, each of these is its own thing. The different displays we do, I guess there's a lot of categorical displays. Well, we did cat and quant on one page. So if you go through here and you try to draw these, categoricals right there, quantitatives there, categorical, bivariate, categorical, to see if there's relationships, bivariate, categorical X, quantitative Y, and quantitative displays right here, where we get into the ideas of like correlation. But that's good stuff. Well, I have class in 20 minutes. And there's a little get-together. We'll be back, and I'll be answering emails. I'm going to go look at emails and run to class. Bye for now, everyone. Bye. We'll be back.